Greetings, everyone. All right, we want to figure out where we can find, or how we can find the volume of a cone using calculus. In other words, what I want to do here is derive the equation or the formula for the volume of a cone using the tools that we've done generated in calculus. Again, like we did with the sphere, if you watch that one, we're going to use a rotation here in order to figure out this volume. Because, a cone is circular on the base. And so let's figure out how we can construct this. Imagine for yourself what I would have to rotate in order to form a cone. What would the area, the region be? What would be bounding it? Well, hopefully with not much thought you were able to think about the fact that we would need a line. It'd be some sort of linear piece. And from this point here, if we were to rotate this around the x-axis, let me make it a little more solid, that triangular region would be a cone. And so, well, let's think about this. If the cone, for the measurements of a cone, we usually have its height and we have its radius of its base. And so if we think, or look at this picture, we can see that the radius would have to be this when we rotate it, and the height would have to be this length right down here along the x-axis. And so those numbers are going to factor in when we try to figure out the volume here. Well, if I'm going to figure out the volume, I'm going to need to generate some draw a rectangle here. And I got my delta x. And I'm going to rotate that region around. Hopefully you can see that we'd be using disk methods, the disk method. So the area of the cross section that I'm going to integrate, we all know that the key to this is to integrate from A to B the area of the cross section. Cross section will be solid circles, and so we're going to use disks. And all we need here is to figure out what equation would bound the upper end of the rectangle. Well, that shouldn't be too hard to figure out. It's just the equation of a line. More specifically, it's the equation of a line that goes through the origin. It's even more specific than that. It's an equation of a line that goes through the origin and has a slope of r over h, rise over run. And so I can write an equation for this as just y equals r over h times x. And that should make some sense to us because the slant height, what is usually called for a cone, is just directly related to the ratio between the height and the radius, and so that equation should make some sense. All right, so remember we want to integrate the area of the cross section, and the area of the cross section here is a circle, a circular disc, and the circular disc, we have pi, has a radius of r over h times x. So this is going to be pi times the quantity r over h x squared. Now remember, r and h are constants, and so when we put this in the volume integral, I'm going to leave the limits of integration off for just a moment. We'll have r squared over h squared, x squared, dx. Just distributing the exponent. And remember, the r squared and the h squared, they're constant, so r squared over h squared is also a constant. Now what about those limits of integration? Well, we're integrating along the x-axis. That's why we have our dx down here. And so what are the left and right-hand boundaries for this region? Well, it starts over at the origin right over here, and it goes all the way out 8 units to the h units to the right. And so we're going integrating from 0 to h. Alright, so now we can use the fundamental theorem to work this out. Remember, we're integrating with respect to x. Okay, so our volume is going to be pi times the integral, and we're going to have the r squared over h squared times 1/3 x cubed, applying the reverse of the power rule. We'll evaluate from 0 to h. And so now if we plugging in 0 yields 0. So I have r squared over h squared times 1/3 h cubed when I substitute an h in there. And notice that we have h squared down here, which cancels with 2 of the 3 h's that are over here. And so now if I just put this in the usual order, we have 1/3, we have pi, we have r squared, and we have that single h left, and there's our formula for the volume of a cone: 1/3 base area, 1/3 pi r squared h, times height. Alright, go study.